title mentions, I will be talking about exploring the near-infrared spectra in order to chemically characterize the inner part of the Milky Way. But before I start talking about near-infrared spectra or inner Milky Way, I will start off with a brief overview about the field of galactic archaeology by showing you this amazing simulation, which is called Vintergatan simulation, which in Swedish means Milky Way, Vintergatan. And this is created by the Cosmologic Simulation Group. And what they have done is that they have made a suite of simulations of different galaxies of masses and sizes. And they have identified at the current redshift, which is 0, a Milky Way mass galaxy, or this galaxy, which is having chemistry as well as the dynamics, everything similar to what we observationally see. And so they trace back how this galaxy would have formed and evolved and understand how the current structure forms. And for that, you can see that there's a lot of violent mergers happening in the proto-galaxy of the Milky Way. And then we know now that there has been a major merger with a Milky Way mass type galaxy at around 8 giga-year ago, which they also see in this particular simulations, and which has shaped up the spiral shape of the Milky Way, as well as the thin and thick disk components, bulge, etc. of the Milky Way. So this is a way the simulations are able to trace back the formation and evolution of the Milky Way. But at the same time, observationally, we need to understand from the current state of the Milky Way how the Milky Way formed and evolved. That is the field of galactic archaeology, where we try to understand the history, formation, and evolution of the galaxies with a particular focus on the Milky Way. And we try to understand the structure and dynamics of different components of the Milky Way. And thanks to the Gaia satellite, which is collecting the astrometric survey and collects the proper motion as well as the position of around billion stars in the Milky Way, we have been able to make this amazing map of the Milky Way in the optical wavelength. And as you can see, there is a lot of extinction, which prevents observations in the midplane of the galaxy, especially towards the galactic center region. And you can see there are different components like the thin disk, thick disk, bulge, etc. marked here. So it is in the galactic archaeology we try to understand or separate out these different components based upon their morphology, chemistry, kinematics, etc. And it also tries to, we also try to understand or unravel the complex and interconnected processes that have shaped the Milky Way. And this can include not only the galaxy accretions that we have seen in the simulations, but also the secular evolution of the Milky Way, which includes stellar migration, gaseous migration, galactic outflows, etc. And all this information is actually encoded in the stars in the form of which acts as a fossil records, because they retain the chemistry of the ISM or the interstellar medium from which the stars would have formed. So studying the stars can indeed help us to understand how the Milky Way galaxy formed and evolved. From an observational perspective, to understand the galaxy formation and evolution, we need to understand the structure of the dust, the structure of the different components, like the thick disk, thin disk, bulge, etc. The star formation history of these different stellar populations that make up these different components, as well as the initial mass function. So for that, for the dust, we need extinction in the different wavelength regime. For the structure, we need to identify the velocities as well as the distances of the individual stars that make up these different components. For star formation history, we need the individual ages as well as the metallicity. And for initial mass function, the mass of the stars. And from an observational perspective, we need different kind of surveys. For example, the astrometric surveys will give us the proper motion, which will indeed give us the velocity of the stars, while parallaxes as well as the apparent magnitude will give us an idea about the distances as well as the extinction in various wavelength regimes. And for getting the ages as well as the masses and the metallicities, we need the indirectly calculate it from the parameters of the stars, mainly surface temperature, surface gravity, as well as metallicity, which can be obtained from the star spectrum. So I'll be talking about the star spectrum. And to introduce star spectrum, as you know, the core of the star is actually burning hydrogen to helium, or nuclear fusion process is happening, and the photon is being produced, which will interact with the cooler photosphere and the elements as well as atoms and molecules which are present in the cooler photosphere, which results in the absorption of this particular photon and will result in this particular absorptions which we see in the spectra. And thus, the spectrum of a star consists of a lot of individual lines which corresponds to different elements as well as molecules, etc. And thus, it contains a wealth of information about the chemistry of these particular stars. And we need to solve the radioactivity transfer equations as well as model the stellar atmosphere, describing the temperature and pressure distribution in the star. so that we can synthesize the spectra and compare it with observed spectra in order to estimate the parameters of the star, including the effective temperature, surface gravity, and chemical compositions. So in this work, I have made use of the spectroscopy made easy tool, which is used to synthesize the spectra, and the Marx models have been used in order to model the stellar atmosphere. But in addition to that, we also need reliable information about these individual lines, which are wavelengths, line strengths, broadening parameters, and hyperplane split information, etc., which are mainly calculated by experimental methods or theoretical calculations, as well as by comparing with the well-known stars like the Sun, Arcturus, etc. And this is compiled in the file called the linelist. So this is also an important part of spectral synthesis. In addition to that, as I mentioned earlier, the fundamental stellar parameters, effective temperature, surface gravity, and metallicity are important in order to synthesize the spectrum. In addition to that, the resolution of the instrument is also very important in order to resolve the individual lines. For example, you can see here, this is the NIRSPEC instrument of the JWST, and you can see there is not much information that is available from this particular spectra, while higher resolution of around 45,000 or 100,000 will give us individual lines. We can resolve the individual lines and can remove the blends so that we can estimate individual abundances from each of the lines. So the resolution also plays a big important role while estimating the abundances and parameters of a star. So here is an example where I show how we determine, for example, magnesium abundance for a star whose spectra is shown, observed spectra is shown by the black line here. You cannot see it properly. But the red line shows the synthetic spectra that have been synthesized, corresponding to temperature of 3,500, surface gravity of 0.7 dex, and metallicity of 0.12 dex. And I am trying to fit this line, which is a magnesium line. And this orange mask tells SME that this line has to be fitted by setting magnesium abundance to be free. And it is also important to make sure that the continuum masks are set properly where there are no absorption lines, so that a synthetic spectrum will exactly calculate the depth of the line from the continuum, not from anywhere else. So there should not be any problems with the continuum at all. So this is how we determine the magnesium abundance, for example, for this star. But why do we need to estimate abundances? This is mainly because these different elements are being produced by different processes in the stars. For example, the alpha elements like oxygen, magnesium, silicon, sulfur, etc., are mainly produced by the type 2 supernovae, which has a brief life of around millions of years. But at the same time, the iron peak elements like iron, manganese, scandium, etc., are mainly produced by type 1a supernovae, which has a long life of billions of years. So there is a time delay between the production of alpha elements like magnesium and iron peak elements like iron. So if you plot alpha to iron ratio as a function of metallicity, you can see that in the older times, which corresponds to lower metallicities, the supernova 2 yield dominates because they have a brief life of millions of years. At the same time, type 1a supernova hasn't gone off yet. So it's mainly the alpha which is dominating in the alpha to iron ratio. So this is the kind of a constant value of alpha to iron ratio. And depending upon the star formation rate, the type 1a supernova starts dominating at different metallicities. If the star formation rate is high, the metallicity at which the turnover happens from the domination of type 2 supernova to type 1a supernova occurs at higher metallicity compared to a lower star formation rate. So this is a general trend that we observe in the Milky Way as well. For example, Reddy and his collaborators in 2006 have classified stars into different components based upon their kinematics, and then showed that they also show some separation in the alpha to iron ratio versus metallicity plots. And as you can see, the high alpha stars are basically thick disk stars, while the low alpha stars are the thin disk stars, while the halo stars are mainly metal poor and also having higher alpha abundances. But with the advent of larger spectroscopic surveys like APOGEE, which mainly observes in the near-infrared wavelength regime and covers a major part of the midplane of the Milky Way with around 300,000 stars, they have estimated the alpha to iron ratio at different bins of distances above the plane and along the plane away from the galactic center. So here, this is the solar neighborhood bin, and at different heights above the plane of the Milky Way, while this is the inner part of the Milky Way, and this is the outer part of the disk. So you can clearly see here that the high alpha disk or the thick disk mainly dominate in the inner part of the Milky Way, while the low alpha disk is extending even to the outer part of the Milky Way. So from this, we can conclude that the high alpha disk or the thick disk has a higher scale height and lower scale length, well compared to the lower alpha disk. So this is how the spectroscopic surveys have been enabling us to understand the patterns in the alpha to ion ratio versus metallicity in the Milky Way. In addition to that, there are also a lot of other information, like, for example, stars which are formed by the last merger, for example, the last major merger, they have a different star formation rate, and as a result, they have a different magnesium to ion ratio. And as you can see here, they have identified these stars to belong to an accreted stellar population from a major merger that happened around 8 giga-years ago by basically from the dynamic classification that they are mainly moving in retrograde fashion compared to the Milky Way stars, which are moving in prograde fashion. While magnesium abundance actually clearly shows there is a lower values of magnesium for these stars compared to the Milky Way in situ population. So this also helps us to separate out the different mergers populations as well. In addition to magnesium or alpha elements that I have talked about, there are many other elements that are being produced by various processes by in the stars and having different timescales. Yeah. Yeah. Mm-hmm. You mean here? Yeah, yeah, yeah. Where? Uh, yeah, yeah. So, yeah. Mm-hmm. Yeah. So that's because of the type 2 supernova being dominating at that range for the stellar population, basically. So that's what I showed earlier here. Sorry. Uh, yeah. So here, when the type 2 supernova dominates, it's mainly the alpha element that is being produced. As a result, alpha to n ratio is more or less constant. So that is why we see in the Milky Way, this thick disk component or thin disk component has this kind of constant kind of stars pattern. But these stars would have a different star formation rate, and they would have had this kind of constant pattern at this kind of metallicities. Uh, the turnover would have happened at very lower metallicities compared to the Milky Way. So that is one of the reasons. Yeah. So in addition to alpha elements, there are many other elements like the carbon, nitrogen, S process elements, neutron star mergers, which lead to the R process elements. So all these different elements also carry information about the formation and evolution of the Milky Way if we can able to estimate accurately these abundances. This has been shown by the Gala survey in 2022, where uh, accreted stellar populations have been identified based upon their kinematic retrograde motion. And as you can see, the red and orange contours represent the accreted population, which have been mainly identified by dynamic criteria. And they clearly show separation from the Milky Way in situ population, which are shown by the black and gray contours in almost all the element pieces. So this means that we need not only the alpha elements or the ion peak elements, but also the other elements also have all this information, which maybe you may not be able to read. These are lithium, carbon, oxygen, sodium, etc. So there are lots of elements that we can get from the star spectrum, which we can use in order to estimate the abundances and separate out the Milky Way component and the outside component, etc. But coming to the inner part of the Milky Way, this is one of the very unexplored part of the Milky Way, mainly because, as I mentioned, there is a lot of dust in this region, which demand observations in the near infrared wavelength. So even in the K band, this is the extinction map in the K band, you can see there is a lot of extinction in the inner part of the Milky Way, but we are able to use the K band observations in order to get the light from these stars in these regions. This represents the bulge envelope of the Milky Way. And then this is the region encompassing the central molecular zone, which is the region which consists of a lot of molecular gases, but the last star formation is found to be much lower. And then there is a nuclear bulge structure, which consists of a nuclear stellar disk, which is a disk-like shape, and the nuclear star cluster, which is one of the most dense star cluster in the Milky Way. So these are all structures which we have identified morphologically, but we are not able to estimate accurate abundances, or we cannot characterize them chemically very well because of the observational limitations. So why should we study the inner Milky Way? Because there are many unexplored structures and stellar population. And in the Milky Way, we will be able to resolve individual stars because it is much closer compared to the other galaxies. And it is unique. This region is unique with an early star formation and chemical enrichment history because of the inside-out formation of the Milky Way. And the strong magnetic field, dense gas, and high turbulence have been detected in this region, which makes the star formation in this region very different compared to the solar neighborhood. So we can expect a very weird kind of chemical signatures, hopefully. And then these are the ideal proxy for understanding initial stages of a typical spiral galaxy formation and evolution. So coming to the nuclear star cluster, as I mentioned, this is a very elusive structure, but it is actually found in almost all types of galaxies, like the late type spiral galaxy as well as the early type complex galaxies. In the case of the Milky Way, this has a mass of around 10⁷ solar mass for stellar mass, and the population is found to be majority of them found to be old and much evolved, like the K and M giant stars. But there have been very handful of studies which have carried out observations in this region, in the nuclear star cluster. And for some reason, they have found that there is a high alpha abundances at the supersolar metallicities for the nuclear star cluster compared to the solar neighborhood, which are represented by the gray points as well as the blue points. So with this study, they tried to say, using chemical evolution models, what kind of processes would have led to this kind of a signature of high alpha abundances at supersolar metallicity. And one of the scenario they suggested was that the early structure of the early inner part of the Milky Way was formed by this is the alpha to ion ratio versus metallicity. And there was an early infall or early star formation episode where the core collapse supernova dominated, and after which the type 1a supernova starts dominating. As a result, there is an alpha to ion ratio decrease, as you can see, which makes this population. But then at some point of time, there was an infall of gas, which could be a major merger, which diluted the gas. And as a result, the iron content reduced. And after some point, the core collapse supernova again starts increasing, which will lead to the formation of this kind of population. And then again, type 1a supernova dominates and forms this population. So there is this kind of a loop which has formed by the infall, early star formation happening, but then followed by an infall of gas, which has diluted the metallicity.
Govind, so
Yeah.
do you have this time scale, typical time scale of this few giga year? Or?
So this case is usually considered to be 5 giga years, I think. Yeah. Okay. Because if you see the next scenario, they have also suggested another scenario where this early star formation happened, but then followed by sudden pauses in the star formation, with pauses which last from 3 to 4 giga years, 2 to 4, etc. So different pauses can also lead this kind of population. Okay. So they were not able to come to a conclusion, as both the evolution models are able to reproduce this kind of populations, the two sets of populations. But the general consensus still is that either the nuclear star cluster could have formed from in situ formation, which is by the funneling of gas through the bar of the Milky Way, or by the accretion of the globular clusters, which were present in the early protogalaxy phase of the Milky Way. No, so that is the thing. In order to understand that, we need to have more observations. With this few sets of observation, this is not conclusive at all. So there are many stars, but chemistry-wise, we are not able to separate or get more information from them. So that is what we are trying to do. So it's basically within the inner part of the Milky Way, within around, it's around 5, it's like 4 parsec basically. And yeah, so photometrically they have been observed, but yeah, it's kind of, so within this only the black hole of the Milky Way is there. So it is there is a lot of stars, but within them, it is the black hole is also included, like that. So it is considered that the bar actually was funneling. It's one of the scenario for the which I have shown here. One of the scenario is that, okay, there have been in situ formation, which is basically the bar has formed, and then it funnels the gas through from the outer part of the galaxy to the inner part of the galaxy and forms the nuclear star cluster. So that is also one scenario. But again, in order to understand that, we have to compare the bar chemical composition with the nuclear star cluster composition. Or if we want to prove that it is not the case, and it is the globular cluster accretion which is happening, we need to compare the globular cluster composition with respect to the nuclear star cluster composition. I mean, in the case of Milky Way, there is clearly a bulge component, which is a part of the, which is found to be an X-shaped morphology. So in the case of the Milky Way, I won't say that it is an unresolved bulge. Yeah. Okay. So, but what are the challenges in carrying out observation? So as I've already mentioned, there is a lot of dust and large extinction, which demand observations in the near infrared wavelength regime. And when I say about near infrared, what I mean is this Earth's transmittance map, where you can see clearly the blue band represent. Okay. The blue band represent the wavelength regimes, which is allowed by the Earth's atmosphere to pass through. And what I define as the near infrared in my work is basically the H and K band, which is from 1.5 to 2.5 micrometer. Now, the near infrared spectra is not as explored as optical spectra because of the late advancement of the near infrared technology and the instruments. So there are many unexplored lines and molecules, etc., which are present in the near infrared spectra that, compared to the optical spectra, which haven't been studied yet. The large distance to the inner part of the Milky Way demand bigger telescopes as well as longer exposures, which is much expensive. And the observable stellar population are also limited to the bright K and M giant stars. But for the M giant stars, which are the cooler stars, there are no reliable methods which have been developed in order to determine parameters and abundances, especially from the near infrared spectra. So when I talk about M giants, these are the range of stars that I mentioned. This is the APOGEE survey. And you can see there are 3000 to 4000 Kelvin. And this is the surface gravity range, which I mentioned as the M giants. So when I say that the M giant spectra is very difficult in the case of optical, this is what I mean. So these are the two stars. These are the same star which is observed by the Gala, which is optical wavelength regime, and APOGEE, which is the near infrared wavelength regime. And in the Gala, you can see that for the cool stars, there is a lot of titanium oxide absorption, which will cause the continuum to go down. And as a result, we are not able to define proper continuum. And as I mentioned earlier, defining proper continuum is very important in order to determine the depth of the lines. And in the case of APOGEE spectrum, we can see that there are many very reliable continuum points which we can use in order to accurately determine the depth of the lines. Thus, near infrared spectra for cool stars is necessary for determining accurate parameters and abundances. Mm-hmm. Yes. Yeah. So yeah, in the work I'm doing is basically 50 stars or 100 stars. So I put the effort into make sure that I select the proper continuum. But we have an automatic tool which will select the continuum. But then I will go and look and check if these continuums are good or not. Yes, exactly. Line-free region and which are not affected by telluric corrections or cosmic rays, etc. It's a bit of an effort. So the main aim of this work that I want to say is that is develop a method to determine stellar parameters of M giant star from near infrared spectra. As such a method doesn't exist yet. Then build a catalog of solar neighborhood M giant stars observed in the near infrared, and thus create a benchmark or reference sample like the Gaia benchmark sample, which have been used by many surveys in order to compare their abundances and parameters with. Then identify useful lines in the near infrared wavelength regime with reliable atomic information, and then estimate abundances for them. Then compare and validate those abundance trends with those from the optical studies of warmer giants, so that we have reliable sets of measurements to compare with, which is mainly from the giants in the local disk sample, which is a solar neighborhood sample of stars, which are warmer than the M giants, but which have very well determined abundances and parameters. And finally, carry out a consistent and systematic analysis of the inner Milky Way stars. That means that I have to observe with the same instrument and analyze with the same method that I've developed and using the same spectral lines, so that I can do a systematic and differential analysis of the stars in the solar neighborhood and in the inner Milky Way. For this, the instrument we have chosen is the immersion grating infrared spectrograph, or IGRINS, which has a resolution of around 45,000 and covers the full H and K band. So it covers the full 1.5 to 2.5 micrometers. And the reductions have been carried out using the IGRINS pipeline package. As I mentioned earlier, the analysis have been carried out with SME and Marx models. And NLT grids were available for corrections for certain elements, not all of them. Now, As I mentioned, stellar parameters are one of the important parameters that we have to determine for a star. And for the MGIRINS, effective temperature determination is possible, but using interferometry, which is like determining the radius of the star, and which in turn can be used to determine the accurate temperature, or using color temperature relations, which have been developed in 1998. But the problem with both these methods is that these are mainly reliable for bright stars and in the nearby stars. And in the stars that we are looking for are the inner Milky Way stars. So these are very far away and not bright enough. And then there is the photometric method called the infrared flux method, which require accurate values of reddening estimates. And uncertainties in reddening estimates can lead to very large errors and uncertainties in the temperature as well. And then there have been methods that have been developed by identifying lines which are sensitive to temperature, like the CO band heads in low resolution K-band spectra and the scandium lines. But there haven't been any valid tests that have been conducted in order to make sure these methods are working fine. So what I ventured into was to identify temperature sensitive near infrared lines. And luckily I found several OH lines which are sensitive to temperature. As you can see here, these are the two spectra, blue and red, with different temperatures, but all other parameters similar. And you can see that OH lines are showing very difference in depth between the two stars. So this means that the temperature, these lines are OH temperature sensitive. But OH lines are also sensitive to oxygen abundance. This means that there is a degeneracy between oxygen abundance and temperature. So which means that we have to fix oxygen abundance while trying to determine temperature from this line. And for that, I relied upon a very accurate measurement of oxygen abundance for the solar neighborhood stars, the thin, thick, and hollow stars from AMASI. And this is the measurements they have made for different components of the Milky Way. And I made a simple functional form of that, which corresponds to, for different metallicities, there will be different values of oxygen for the thin and thick disk component. So the assumption that I have to make is that whether the star is having a oxygen abundance, which is following a thin disk pattern or a thick disk pattern. So the method follows like this. I will start off with the temperature, log G, metallicity, etc. for all the stars at the same value, and then oxygen abundance based upon an assumption of thin or thick disk. And then I will fit the selected OH, iron, carbon, nitrogen, and CO lines, and estimate a new sets of temperature, metallicity, microturbulence, carbon, and nitrogen from this set of lines by using SME. But then you can notice that I haven't got a new value of log G, because log G is very difficult to determine. So I rely instead on a YY isochron or Yonsei isochrons to determine surface gravity from the new sets of temperature and metallicity. To explain this and why I chose the 10 gigayear, you can see here, for the giants, there is a big overlap between different ages. So even for a young age and a old age, the isochrons are pretty much overlapping in the case of the giants. So once we know the temperature and metallicity, we can easily assume a log G value. So this is how we set the log G value in this method. And then we check if the new sets of parameters are different from the previous step of parameters. And if it is different, we will update the new log G value from the isochrons and the oxygen values based upon the new metallicity that we got from the previous run. And then we will do this cycle repeatedly until and unless the new sets of parameters are very similar to the previous run's parameters. And that's how we get the final sets of temperature, surface gravity, metallicity, carbon, nitrogen, etc. So now is the time to check this or validate this method. For this, I selected 6 nearby MGN stars with very reliable angular diameter temperature. These are very nearby stars and bright, and from the IGRINS spectral library. So these spectra were already available. And then we submitted proposal to observe 44 solar neighborhood MGN stars, which also was measured or observed in APOGEE survey. So the method, as I mentioned, is used to determine the parameters. And for the 6 nearby stars, we found temperatures to be consistent within 100 Kelvin for different methods, including the color temperature relation as well as the interferometry. And for the 44 solar neighborhood MGN stars, there is a reasonable agreement between the values that we got and with APOGEE values. So it is clear that our method is working very well. And thus now we have around 50 solar neighborhood MGN stars with IGRINS spectra, which can be used as a catalog of benchmark sample. And in addition to that, we further did a validation by using open clusters, which are cool MGN stars in the open clusters, which are mentioned here. And we found that our metallicities for these open clusters are very narrowly distributed, which indicates that our parameters are, again, very valid here. So if I come back to the aims, we have developed a method to determine stellar parameters. We have built a catalog of solar neighborhood M-giant stars, which are 15 in number. And the next step is to identify lines in the near-infrared wavelength regime. And for this, we explored a dot of lines. And I've started off with this work we have done with phosphorus. So phosphorus is one of the key elements of life, and it's mainly explored by many of the exoplanet studies nowadays. And its origin or formation sites, like we don't know exactly where this particular element comes from, what kind of stars. And the main reason is that there is an absence of measurable lines in the commonly used wavelength range, which corresponds optical. So we have to rely on near-infrared wavelengths or ultraviolet wavelengths for this. And the chemical evolution models at the same time, with the very limited number of studies, have found that the primary production of phosphorus could be through the core collapse supernova of massive stars. In addition to that, there have been many stars which are enhanced in S-process elements which are found to be enhanced in phosphorus as well, whose origin is again unknown. So I explored this line, which is at 16483 Armstrong, which is also blended with a very strong CO line, as you can see here. But I made sure that I fit the surrounding CO lines very well. So you can see in all the cases I have fit, these are the different stars, and I have made sure to fit the surrounding CO lines very well, so that this line, which is blended with this phosphorus, is also fitted properly. And you can see that as the temperature increases, the contribution of the phosphorus also increases, which means that the CO line becomes weak. So this is how I determined the phosphorus abundances for the around 40 stars in the solar neighborhood. And I found that the abundance that we determined is corresponding very well with the previous literature values, and also with the chemical evolution model trends that were produced by Sescuti and 2012. And also, we also found two S-rich stars again, which are enhanced in phosphorus. So this is all consistent with the previous literature, and we have added more number of stars into the phosphorus studies. In addition to that, we also proposed what kind of stars will be suited for observation or estimating accurate abundances of phosphorus from this line. And as I mentioned earlier, the CO lines become weaker as temperature increases. So this line is not suitable for M-giant stars, where the CO lines is much stronger. So this line is only suitable for estimating phosphorus abundances for the K-giant star. So that is one of the work that we published. And the next one is fluorine, which is again one of the element which is not whose origin or formation sites are still under debate. There are lots of suggested sites like the rapidly rotating massive stars, thermal pulses in asymptotic giant branch stars, core collapse supernovae, novae, all of which have different time processes. And the main again reason is that there are no strong atomic fluorine lines at optical or infrared wavelengths. Only molecular HF lines were available in the near infrared. And the most commonly used line is the 23358 Armstrong line. And the studies that I have carried out with this particular line at 23358 have shown that there is a significant enhancement in fluorine at supersolar metallicities. And unfortunately, none of the chemical evolution models with the sites the sites which are under debate are able to reproduce this enhancement in fluorine abundance. All of them are going down or going constant. So this indicates that there is something wrong with the measurement of this particular abundance from this particular line. So I started exploring what other lines are available in the near infrared. And there are apparently 10 different lines of HF which are available in the near infrared, especially getting stronger for cool M-giant stars. So these are two different stars on this one and this one. And this is the increasing wavelength, and they are divided into two panels. And as you can see, the lines get stronger as the wavelength increases. And this is the line that is commonly used by many of the studies which have shown the enhancement in fluorine. So I estimated the fluorine abundance from each of these lines. And I found that for these stronger lines, there is a significant enhancement that is being shown. And as shown by this running median values that we determined for each of the lines. So the weaker lines do not show this enhancement in fluorine, but the stronger lines do show that. So this again is investigated if these lines are saturated at the longer wavelengths by changing the microturbulence value. And you can see that there is clear difference in the fluorine abundance as the microturbulence changes. While for the weaker lines, this change is not seen, which indicates that these lines are strongly saturated at the longer wavelengths. So we only chose these lines which are not saturated and estimate the fluorine abundance. And you can see that there is no more this significant enhancement that has been seen using the line at 23358 Armstrong. So this need to be much more explored, as we have not have many lines in this, many stars in this region. So there is still work under progress in order to estimate more abundances from more number of stars at the supersolar metallicity range. In addition to that, other elements have been identified. As you can see, there are many alpha elements with strong lines that have been identified, magnesium, silicon, calcium, sulfur, etc. Then there is odd Z elements like sodium, aluminum, potassium. And then there are iron peak elements like cobalt, nickel, chromium, scandium, etc. And finally, there are also neutron capture elements like copper, yttrium, cerium, neodymium, ytterbium, etc. So these are all the different lines that we have manually found to be working very well. And we are able to reproduce or synthesize these lines very well. So coming back to the aims again, so I have now done this part where we have identified at least 21 elements and estimated abundances for them for the 50 solar neighborhood stars. And now the next step is to carry out a comparison and validation of these abundance trends. So here is the guild abundance trends from the optical studies of warmer giants, as shown by the gray points here. So as I mentioned, the guild studies is mainly the optical wavelength regime, so it doesn't have fluorine or ytterbium or sulfur, etc. So these are mainly near-infrared lines that are available in the literature. So you can see that this is basically the trend that we expect from these different elements. And this is a way to show how these different elements actually have our current understanding of these different elements, what are the formation sites of these different elements. And when I overplot the 50 solar neighborhood M giant stars, you can see the red lines are the red points are the thin disk stars, and the orange points are the thick disk stars. And you can see clearly that our trends are matching well with the optical studies of warmer giants. And we also see the thick disk trend to be following the lower envelope of S process element, like yttrium or cerium, etc. And at the high alpha values for the magnesium, silicon, etc. for the thick disk values. So like I mentioned, there are alpha elements, there is odd Z elements, there is iron peak elements, there is neutron capture elements. So these are all the different elements that we were able to estimate for these 50 stars. So that is also done. The next step is to carry out a consistent and systematic analysis of the inner Milky Way stars. As I mentioned, we have to observe with the inner Milky Way stars, again with the same instrument. So this is a work in progress. But we observed stars in the inner part of the Milky Way with the latitude of +1 degree and longitude of 0 degrees, which is called the BP1, B+1 field. And the nuclear star cluster, we also proposed for observation of around 20 stars. And this is how we selected the stars in the color magnitude diagram. For the BP1, around 10 or 11 stars, and while the NSC around 20 stars. 7 BP1 stars have been observed. 20 nuclear star clusters have been observed. With the BP1 stars, I estimated the stellar parameters using the same method as mentioned earlier, and then compared with the solar neighborhood stars, as you can see here. So they are lying on the exact isochron metallicity trends as we have expect them to be, because it is mainly based upon the isochrons also. And when you compare the abundances that we have determined for the 7 BP1 stars, which are represented by this black stars, you can clearly see that for the alpha elements, there is this BP1 stars are following the thick disk, even at the solar neighborhood or the supersolar metallicity regime. So they are in the lower metallicity, they are following the orange points, and the supersolar metallicity, they are lying a bit above the thin disk. And in the case of the cerium or the S process elements, you can see they are again following the thick disk trend. So this means that, and this again is shown by the mean value of magnesium, silicon, and calcium for the solar neighborhood stars as well as the BP1 stars. And you can clearly see here that the BP1 stars clearly follow the upper envelope or the thick disk trend of the solar neighborhood. This means that the chemistry of the inner bulge stars are not very different from the solar neighborhood thick disk stars. So we need more number of stars in order to confirm this, but this is a very good indication by a differential spectroscopic analysis that the chemistry of the inner bulge stars are strikingly similar to the solar neighborhood thick disk. Now, I will also show some preliminary result for the nuclear star cluster. For the magnesium, 3 lines have been used, and these are the 20 stars, and the blue points represent the BP1 stars that I have shown earlier, and the black stars are the nuclear star cluster. And again, you can see that they are following the upper envelope, but the nuclear star clusters are mostly metal rich. As you can see, there are no stars in this part. Again, for the silicon, we find the same kind of upper envelope trend. And for the calcium with around 10 lines, we are able to see this kind of trend, which is similar to the BP1. And from the mean value of magnesium, silicon, and calcium, it is very clear that the nuclear star cluster stars are following the BP1 or the inner bulge stars, which again shows that there is not much difference between the nuclear star cluster stars and the inner bulge stars as we expected. And this also brings forth the question about whether these stars, which are found to be enhanced in alpha abundance by Tosbro et al. 2020, where they suggested various scenarios, we are not finding those kind of enhancement in alpha abundance. Though we only have 2 stars, we are doing a very systematic and consistent analysis, which makes sure that there is not much of a mistake in that. So we have got more stars now observed being here. So that will be interesting to suggest what exactly is happening, whether it is a simple star formation episode which goes on like this without any pauses in star formation, or is it just so that is one interesting thing that is going to happen soon. So in addition, in order to understand if there are other kind of formation scenarios that could be contributing, like the globular cluster accretion or in situ formation, we need more number of stars and more number of chemical compositions, not just alpha elements. So more elements will be coming out soon with the neutron capture elements as well as fluorine, sodium, etc., which will help us understand what kind of processes would have resulted in the formation of nuclear star cluster. So coming to the aims, which will become now the summary, you can see that this work is still in progress. So all other things have been done. And so now we have a very good base where we can observe more number of inner Milky Way stars and carry out a systematic and consistent spectroscopic analysis. Coming to the future works, I would like to venture into analyzing the low resolution near infrared spectra of M giant stars using the instruments which like the TANSPEC or chemos, because knowledge from high resolution spectroscopy will be very useful in developing methods of parameter determination and abundance determination for low resolution spectra. And machine learning tools will have a strong impact in this. And the benchmark sample that I have made will be very useful in making up this kind of machine learning tools. In addition to that, I am also planning to carry out near-infrared spectroscopic analysis of inner Milky Way clusters, because there have been recent observations of Lil-1 cluster, which is found in the inner part of the bulge, which is also having supersolar metallicity stars. So it will be very interesting to compare this cluster with the nuclear star cluster stars. And then it's also very important to decipher the connection between the gas, dust, and stars in the inner Milky Way using multi-wavelength data, and radio observations, sub-millimeter, mid, and far infrared observations are very crucial for this. Then, as I mentioned in the beginning, the first slide I showed, there are many models and simulations where we can trace back the formation and evolution. And if we can zoom in into the inner part of the Milky Way, we will be able to also compare observations with simulations. Finally, there are many future surveys and observing facilities, including the Moon's survey, which is going to come soon, which is also observing the inner part of the Milky Way, and will have lots of number of stars compared to the 7 stars or 20 stars that we have. And the method that I have developed will be useful for this kind of surveys. And then there is 30-meter telescope and accompanying instruments, which will mainly use as the near-infrared wavelength regime. And also the India's 10-meter National Large Optical IR Telescope, which also has many instruments, which are similar to the instruments that I've already worked with, and I can propose many science projects for them as well. Thank you. Mm-hmm. Sorry? No, no, not yet, because I recently went to a conference where I found this cluster being studied by another team, and they have shown fluorine and sodium abundances to be high, which I found for the nuclear star cluster. So even though they are not using the same method or lines that I am using, I have asked them if they can send me the spectra, and then I can work on it. So we don't have the spectra from IGRINS for these stars, but we are planning to apply for time for that. Yeah. Yes, exactly. So it will help either way, like whether global clusters contributed or if the other way. Yeah, yeah, it'll be nice.
Yeah, so something related to cosmic rays, like for example, we find the cosmic ray proton spectrum softer than the helium spectrum. Okay, so helium is harder. So people do expect that there can be a population of stars, some kind of, where helium is in abundance compared to protons. Okay, so do you find any sites where the helium in some population of stars where helium is in abundance?
So the problem with the near infrared spectra, we haven't yet found any helium lines.
Okay.
So we don't have helium measurements for the stars at least.
Okay.
So I think optical lines or the UV lines are the commonly used helium.
Yeah, because the thing is, like, the helium abundance because this population of stars is completely missing from the sources of cosmic rays. So something.
Yeah, but if I find some helium lines, it will be interesting to look at. Not yet. Okay. So not in this wavelength range, at least. Mm. 10,380, right? Okay. So this, it will be interesting to look at that actually. Yes.
How much the low resolution spectra will be useful for getting the abundances?
Good question. So yeah, so this is a like the one I've shown you 2700. It doesn't have any information, but still we were able to use such chemo spectra to like distinguish between stars. And with the latest machine learning tools, where we can train upon very accurate temperatures or spectra, we can actually develop even identify small changes in the low resolution spectra. So I hope we can develop some tool with a good high resolution spectroscopic like set of stars and very well determined abundances and parameters. We can train them on that and then try it on test them on the low resolution spectra. And there may be a chance. I am not hopeful, but
So the tool you have developed at the time, have you checked if you decrease the resolution, how sensitive is the parameter estimations?
No, not yet. So this is a project in still in mind, which hasn't developed yet. But if we get time, we will definitely try to do that. With the SME, we can actually make the resolution smaller and see what kind of details we can see.
And JWST, like low resolution, medium resolution.
Yeah. No, I haven't used JWST at all. It was just a demonstration of how the resolution affects. Yes. Yeah. But still people are able to get some things from that. Yeah. And advantage of low resolution is that we can observe more number of stars. Example, like CMOS is an IFU spectrograph. So you can observe many number of stars at the same time. And there is already a work where they have observed around 300 stars in the nuclear star cluster with the CMOS, but their errors are very, very high. So I would like to test on this kind of spectra. So the chemo spectra is around 4000 resolution, which is good compared to 2700.
And whenever you are fitting these lines, do you have this V sin as a parameter or is it fixed?
No. So in the case of giant stars, the rotation is, and low mass stars, the rotation is not that much of a significant.
Okay.
So
Flow
rotators. So the Vmac parameter, micro turbulence and micro turbulence will take up the broadening scenarios. Yeah. That is one advantage of giants.
You would also, the OH lines you would also get from terrestrial origin, I suppose? OH lines?
No, not much.
Not
no.
many. From the water vapor lines?
No.
Not much.
No,
Okay.
at least we don't see that. I think it is in the optical wavelength
In the optical wavelength.
not in the near infrared at least. We don't see it.
Okay.
Yeah. Yeah. So for example, if I can, if I can try to, so if I have tried to show here the telluric, I don't think it is clear here. The orange line here is actually telluric. So I made sure I choose the lines which are not affected by telluric. So this is the orange lines are basically the telluric. So for example, here there is a telluric being affecting, but we are able to do a proper correction of that. That is why the fit is pretty good in that sense. So yeah. So there are lines which are affecting, for example, this here. So if it is at the center, then I'm not very sure about that, and I will neglect that line. Continuum. Yeah, continuum, I make sure that I select the lines. So I do first round of fitting, and then I go and check if there are tellurics in that line. And then I remove those continuum. So it's a big effort, basically. But that is the advantage of having only 50 stars.
My question is on this NLT analysis.
Yeah.
Why do you go for NLT analysis?
Why?
Yes.
Because there may be cases where these elements would be formed deep inside the, not in the photosphere, and there could be effects of non-LT. We are assuming LT to be the best case scenario, but there could be effects of non-LT which could be causing the abundance to be totally wrong. So for simplification, we are using LT.
Did you find some?
Yes. For example, the sodium line are pretty much affected by the NLT corrections, and even okay, the plot I showed of the accreted stellar population, even though I have only shown the 1D LT case here, there is also a 1D LT, 1D NLT case here. But actually, there is a 1D LT case. Actually, there is a side plot.
Did you overlap? No overplot?
No, not this one. But I'm just saying that there are NLT effects for different elements. And for my case, there have been NLT difference of at least 0.1 to 0.2 dex in some cases. Not all the lines or not all the elements, but certain lines and certain elements. Yeah.
Basically, the simplistic assumption is LT. that's
LT takes less time, and yeah, and these corrections are also just departure coefficient. So this is just a post-processing kind of correction based upon trends and everything. So this is not totally including the NLT analysis actually.
So other question is on this continuum, level of continuum. In one case, can you go in your slide?
Yeah.
The continuum where you have shown two continuums, right?
You mean okay, the magnesium?
Yes.
Okay. Sorry. This one. This one?
Sorry.
Okay.
No.
Uh,
In one case, it is below the continuum, right?
okay, so is the one that I showed just now, or I'll try to reach there.
Yeah.
Okay. The Gala and
Yes. Gala Anderson.
okay. Yes, this will be. Yeah.
So here you see in one case it is very below the continuum level, right? So in other case it is above the continuum level, even shifted, right?
Yeah, this is so this is because this is APOGEE spectrum that I downloaded from it's APOGEE pseudo continuum normalized spectra. So it is not very well done actually continuum. So I just showed it to show that there are good continuum points. So the APOGEE, there is a set of, because APOGEE has 300,000 stars, so they have done a very rough job of continuum normalization. I'm not using this star spectra at all. This is just a demonstration that there are no strong absorption lines which will cause it to go down a lot. So this continuum is wrong actually.
That's I'm asking you.
Exactly. You're right. Yeah.
So last question. So as far as low Gaussian spectroscopy is concerned, so you can just study this machine learning. You can apply the machine learning to see the features.
Yeah.
Otherwise, it's very hard to determine the basic parameter very accurately.
Yes.
Even temperature, abundance, it's very unreliable, I would say.
Yeah.
But these features you can study, right?
Yes.
You can compare with the other.
Yeah. So I have done such a study with chemos where I've separated.
Even people have done for the LAMOST.
Yes.
Some papers are on the LAMOST. They have studied thousands of stars.
Yeah.
Line.
So yeah, I will try first the impossible, and then if it doesn't work, this is the best thing to do, I guess. Yeah, that's true. Yeah.
How many these elements you have?
Yes. It's actually publicly available if I'm not wrong. We just have to integrate it. So these are the, yeah. So I mainly see differences in the case of sodium, magnesium, and silicon is not much of a change for the lines that I use at least. Yeah. So this Amasi, he actually has a paper where he has. I think so, yeah. Or I think he's very nice person. So if you contact him, he'll just easily give you, and yeah.
Okay, so if there's no further question, comments, let's thank Govind for his wonderful talk. So he is here for tomorrow also, tomorrow afternoon until, and of course he will come back for his new assignment, new position here after some time. So see you all, and thank you for